So till now we have discussed about the waves between paraplanes. First one we have discussed about TE waves. First we have discussed about TM waves. Then we have discussed about TE waves, and now finally we are left with one, that is the waves between paraplanes, TEM waves. Here we are going to discuss about the propagation of TEM waves between paraplanes. The TEM wave become a TM wave when m is equal to 0, and the field equations that we have derived in the last class, that is from equation 19, 20 and 21, will now become as follows, that is uh, the HY component, that is Y component of magnetic field, X component of electric field, Z component of electric field will be 0. So these are three are the conditions for TEM propagation. Okay, so equation 33, 34, and they are numbered by because they have a condition. Since epsilon is equal to 0, we are not numbering it. So these three equations represent the condition for TEM propagation. Now one additional piece of information that we gain from equation 4b, that is in the first class we have discussed, that is in the introductory class. It states that dou by dou x of Hy equal to 0. This equation states that the y component of magnetic field, that is Hy, is a constant for all value of x, or for all positions between the planes for a particular z value. Now from equation 5 in the introductory class, it is also possible to write that for a good dielectric condition, we can write this equation, and from that we can write that gamma square plus omega square mu 1 epsilon 1 equal to 0. So I think after writing this sentence, that is from equation 5, it is possible to write that for a good dielectric condition, can straight away write this equation. No need of writing this equation. Okay, now that equation that is now numbered as equation 35 is actually equation 10 that is previously obtained for TM waves with m equal to 0. Now with the above equation we can write the propagation constant gamma for TEM wave as gamma equal to j omega root of mu 1 epsilon 1, and the attenuation constant alpha is equal to 0. So since m equal to 0, cutoff frequency given for TM waves becomes 0, so that TM wave propagate without attenuation between uh, the perfectly conducting planes for all frequencies above that of 0. Okay, so that is how TEM waves propagate. So this sentence is very important. That is, the TEM waves propagate without attenuation between the plates for all frequencies above that of 0. Now by using equation 26, we get the expression for the x component of electric field as epsilon x is equal to eta 1 b2 e raised to minus j beta z sin omega t. So you can write straight away, write this as this, no need of writing this equation. Now comparing equation 33 for Hy, we get the expression for Hy as b2 e raised to minus j beta z sin omega t. Now this shows that epsilon and h are to be related by the factor eta 1, which is nothing but intrinsic impedance of the dielectric. The value of beta corresponds to free space transmission. Since there is no component of electric field tangential to the conducting planes, we can say that these planes have no effect except to limit the area of the wave. TM waves are those which would appear in the fields present along a dissipationless transmission line, that is without any loss. Equation 33 and 37 show that for a TM wave, epsilon is z equal to eta 1 Hy. The power propagating in the z direction between the planes per unit within the y direction is given by Poynting radiation theorem from field concepts, and Poynting vector is given by P is equal to half eta 1 Hy square into A into 1 watt per meter of width, that is equation 8. Now the area of the path being a into 1 meter. Now the pointing vector direction confirms positive is the direction of this power flow. That is, direction of pointing vector actually gives the positive is the direction of power flow. Now the maximum value of potential drop between the top and bottom plates is given by integral of electric field as this one. So it is enough that you write this expression only. No need of writing this. That is, V cap is equal to eta 1 B2 A. That much volts. That is the maximum value of potential drop between the top and bottom plates. Now, the current flowing in either the top or bottom plate per unit Y width is found by considering a path ABCD as shown in the figure. Since the plates are perfectly conducting, all current will flow on the plate surface and the field intensity Hy will exist between A and B in the dielectric. That's because Hy will not vary with X. Since the magnetic field is not penetrating into the conductor, no magnetic field intensity will exist along the path DC in the perfect conductor. So, that current flowing per meter of width in y direction is given by I is equal to closed integral H dot L. You are just closing that loop, that is AB, BC, CD, DA. So, there being no normal H components. So, the maximum value of current per unit width of the plate will be I cap is equal to B2. So it is enough that you write, hence the current flowing per meter of the width in y direction is the current enclosed by the path ABCD. If you want, you can write this expression, otherwise you can skip, but you have to write the maximum value of current per unit width of the plate, that is I cap equal to B2. Since the planes are lossless, the power transmitted along the planes and supplied to the load is given by the expression, that is the transmitted power, that is the power that is supplied to the load is given by the expression P is equal to half V cap I cap, that is again equal to half eta 1 B2 square A per unit width in the y direction. Since the maximum value of Hy is B2, the power delivered to the load in terms of current and voltage can again be expressed as P is equal to half eta 1 Hy square A watts per meter of width. Now this is identical with the power shown to be conveyed by electromagnetic field when we use Poynting vector, which is given by equation 38. So finally we can conclude that energy transmitted along a lossless conductive path is conveyed by electric and magnetic field in the region, the voltage and current being present merely as evidence of existence of the field. You can write that sentence also. Okay, thank you.